All right, I'm working on extra credit webinar for Friday. I'll send out an email. Either you can come here, we're going to have pizza and drinks and get extra credit, or if you can't make it here, you can zoom in from wherever you're at. If you're zooming in from someplace else, you'll have to write a paragraph on your thoughts and stuff on the webinar to get your extra credit. So the advantage of coming here for it is you get pizza, drinks, and you don't have to write anything. You just get your extra credit. And that's going to be at 6 o'clock on Friday. And the email will be coming out soon. All right, we're going to do some problems in chapter 12. All right, so when you have a compound that is named eugenol and not sodium chloride or potassium chloride or something that is on the periodic table, it's going to be a molecular compound containing carbons, hydrogens. These are molecular compounds. When you are a molecular compound, your I value is always going to be 1. All right, so if you've never heard of it before, the I value is always 1. It is some sort of organic compound. All right, and so it's a yellow liquid dissolved in ethanol, has a boiling point of 255 degrees Celsius. All right, so we know that this very high boiling point means you have a very low vapor pressure, very little vapor. If you spilled this someplace and you came back and you spilled the same amount of water, the water's gone, that stuff's still there. Has a very low vapor pressure. It would take a long time for that to evaporate. All right, so it is non-volatile, all right, because it does not evaporate quickly. So if you have a very low vapor pressure, you're going to be non-volatile, which means you don't have very much vapor. All right, if you gasoline is both volatile and flammable. All right, so flammable means you put a fire to it, it catches on fire. Volatility means how quick it will evaporate, how much gas is in there so that you can ignite it. Again, when you burn gasoline, you're not burning the liquid, you're burning the vapors. All right. So vapor pressure lowering at 20 of the solution. That contains 8.56 grams of eugenol in 50 grams of ethanol. All right, and so your vapor pressure of ethanol, which is your solvent, is 44.6 millimeters of mercury at 20 degrees Celsius. So what we're going to do is we're going to take 50 grams of that and add 8.56 grams of eugenol. All right, and you have what is called a vapor pressure lowering. So your delta P is a vapor pressure lowering. That is your pure, the little circle there is pure of your solvent, which in this case is ethanol, times the mole fraction of your solute, which this time is eugenol. So all you have to do is convert this to moles. So divide that by the molar mass. They give you the formula, 10 carbons, 12 hydrogens, 2 oxygens. You have ethanol, also needs to go into moles. They give you the formula, 2 carbons, 6 hydrogens, 1 oxygen for ethanol. So you just put those both in moles, find your mole fraction of your solute, that goes here, times the 44.6, which is your vapor pressure of pure ethanol, and then you will have your vapor pressure lowering. And so here are all the calculations. Divide by the molar masses, you get your moles. All right, so again, so for mole fraction, we have to add these up and get the total moles. All right, so we're going to do that next. Add those up, you got your total moles. So now you want the mole fraction of your solute. So you're going to take the 0.0521 moles and divide by the total, which is 1.137. That will give you your mole fraction of your solute. So 0.04581. So now you take your 44.6 millimeters of mercury. That is your pure solvent. All right, the little circle up there means pure. So ethanol all by itself has a vapor pressure of 44.6 at 20 degrees Celsius. All right, and this is the mole fraction of your, they say solvent. That is not correct. All right, so of course they took the solute mole fraction. So that should say solute. So the vapor pressure lowering is the mole fraction of your solute times the vapor pressure of your pure solvent. All right, and so you see that you have a vapor pressure lowering of 2.04 millimeters of mercury. That could be the question. The question could be, calculate the vapor pressure of the solution. And so on the test, you will get both questions. What is your vapor pressure lowering? What is the vapor pressure of the solution? All right, well, it was 44.6 and it lowered by 2.04. So you simply take your 44.6 and subtract your 2.04. It is a vapor pressure lowering. And your answer is 42 point, it would be 56, but 1 decimal, that rounds to 6 millimeters of mercury. So if you're doing the sig figs, it is 42.6. If you're not doing sig figs, then it's 42.56. All right, and so you have a vapor pressure lowering, which means that this solution has a lower vapor pressure than it had when it was pure. All right, so all right, so this equation, they give it later correctly. Anytime you have this equation, make sure you have an I in there. It's going to put that in there later. I don't know why it's not in there every single time they show it. Your I is ions in solution. So remember, if it's organic, all right, so this is a bunch of nonmetals. So organic, carbon, hydrogen, oxygen, nitrogen, whatever, a bunch of non-metals, molecular compound. It could just be NH3, whatever. So now you're saying anything that is organic or molecular, your I value is always 1. If you are ionic, it depends on your formula. So if you are ionic, then you have a metal with a non-metal. All right, and so I is not 1. All right, and so if you have NaCl, then your I value is 2. If you have Na2SO4, your I value is 3. It is ions in solution. It's Na plus Cl minus. It is 2 Na plus and 1 SO4 minus 2. So you have to be able to get your I value from your ionic compounds. All right, so you have a boiling point elevation. All right, boiling point elevation. The boiling point always goes up. So you need to know when you're calculating your delta T sub B, they don't usually ask for what is delta T sub B. They ask for what is the boiling point. Well, you have to calculate delta T sub B, and whatever the boiling point was, it is this much higher. That's how much higher the boiling point is. It's a boiling point elevation. When you have a freezing point, again, the I value should be here. When you have a freezing point, it's a freezing point depression. Depression means it's going down. And so when you calculate your delta T sub F, that is not your freezing point. That is how much your freezing point went down. So whatever your freezing point was when it was pure, it went down by the delta T sub F number. All right, so when we have a problem on your C sub M here, your M, this is, when I write this, this is C sub M, which is molality, which is moles, solute, kilogram, solvent. All right, so on the test, you're not going to see it written with an M. You're going to see it as C sub M. That's the same thing, just how you want to designate it. So C stands for concentration, little m, molality. If you just put an M there, some people might think that's a mass. It is not a mass, it is a molality. So we put C sub M. Not sure why they're not using that in that PowerPoint. All right, so now we want to know what the freezing and boiling points are of this eugenol. This is the solute in diethyl ether. So they have to give you the pure boiling point and the freezing point. So the freezing point here for your diethyl ether is minus 116.3. We know that it is going to come down from that. The boiling point is 34.6 degrees Celsius, and we know that the boiling point is going to go up from that. So you need to put those words together every time. You've got your freezing point depression, that's how much it's going to go down. You have your boiling point elevation, that's how much it's going to go up. All right, the freezing point depression, boiling point elevation constants. So you have your equations, and they both have, so your delta T sub F is equal to I K F C sub M is the way I write it. The I value is 1 because we're doing organics, things that start with carbon. Everything's a non-metal. I value is 1. Your KF, that's your constant. All right, so they have to give you the constants. And then C sub M is what you have to calculate. That is your molality. All right, except you don't have to calculate in this. They say that the solution is 0.575. So they make this question very, very simple. You don't have to calculate your molality. Usually the hardest part about this problem is to calculate the molality. All right, so you have a 1, you have a freezing point elevation constant, freezing point depression constant, and a boiling point elevation constants given here. So 1.79. And then they give you your molality, 0.575. All right, and so your constant is given in degrees Celsius per molal. That's why your concentration has to be in molal so that they cancel. And the I value has no units. So that's your freezing point depression. You multiply those two numbers, and that's how far it comes down. Boiling point elevation, everything's exactly the same, except you put in your other constant, 2.02. So delta T sub B is your 1. Now it's your 2.02, and your molality is 0.575. All right, and that's how much the boiling point is going to go up. So note the question. Well, is there a question? Eugenol solution. What are the freezing point and boiling point of the solution? All right, so the reason why a lot of people get this wrong, but they do it right, they calculate the delta T sub F and they say that's the freezing point. That is not the freezing point. That is the freezing point depression. So you have to go to the negative 116.3 and go lower than that by this amount that you calculate. If you say the boiling point of the solution is your delta T sub B, that is wrong. That is how much it went up. So you add that to the 34.6. So make sure you're answering the question. They're not asking for what is the amount that the freezing point came down. They're not asking what is the amount the boiling point went up. They're asking for the freezing point and the boiling point. So once you get your numbers, so your freezing point, when you multiply those together, you got 1.03. That's your freezing point depression. And so it was negative 116.3. Now it's negative 117.3. Can't see the negative. It's hidden by the green thing there. Back one. Okay. All right. So that's a negative. You can see it before it closes it up that it was a negative 117.3. Same thing with your boiling point. Once you calculate it, you know that your boiling point elevation is 1.16. That is definitely not the boiling point. That is what you add to the boiling point. So you have your 34.6, you add your 1.16. Your boiling point for that solution is 35.8. And so this is very useful in your car, the radiator, the fluid in there. So you add this fluid and it makes the boiling point of that solution go much higher, which is great when it's hot outside and you don't want to overheat your car. And it also has a freezing point depression, which is great because when it gets cold outside, you don't want your radiator to freeze. And so this is a great application for coolant in cars. All right, so that is the easiest equation you're going to get, probably you're going to get for freezing point depression. Here is the usual. In a freezing point depression experiment, the molality of the solution, you have 58.1 milligrams of something you've never heard of. That makes it organic. As soon as you've never heard of it before, it's not on the periodic table. The I value is 1. 5.00 grams of benzene. Maybe you've heard of benzene because it's a carcinogen, but again, it's organic. The I value is 1. It's not on the periodic table. All right, and so we determined that molality, so it's 0.0784. And you did this by doing a freezing point depression. So you go into the lab, you do your freezing point depression, you can calculate the molality from your freezing point depression. All right, but the question is, what is the molar mass of this organic compound? All right, and so the online freezing point depression experiment was doing exactly this. You were given an unknown. You had to find out what was the molar mass of the unknown. They tell you what it is, but it's not helpful because I don't know what that is. I couldn't tell you how many carbons, hydrogens, oxygens that has. So they pick something that you can never tell what the molar mass would be unless you calculate it. So you have to know what molality is. Molality, moles of solute per kilogram of solvent. You also have to remember, how do you find your moles of solute? Well, we did it a bunch of times already. You take the mass in grams and we divide by the molar mass in grams per mole. And so the first one we had this much mass of this thing, this much mass of the other thing, is the first thing, convert it into moles. How do you do that? You divide by the molar mass. All right, and then here we just simply need kilograms of solvent. All right, and so we have one unknown. We have the molality. They give it to us. It's right here. So we know this number. The mass is how much we added here. We just got to get rid of that and put times 10 to the minus 3. We have our mass in grams. We have 5 grams of benzene. And so if we say we want to convert that to kilograms, we have 0.00500 kilograms. Then we have this. So we have 3 of the 4, and that's what you have to have. You have to have 3 of the 4. You can only have one unknown. And then you solve for the last thing. So you have your molality given to you as 0.0784, and that is in moles per kilogram. And that's equal to your mass, which is 0.0581 grams, converting the milligrams to grams. And then the molar mass, that is what we are looking for. And the kilograms of solvent, which is 0.00500 kilograms. All right, so some people can set this up and then they can't solve for molar mass. All right, so what we have to do is we have to multiply both sides by molar mass. And so the molar mass in the denominator cancels the molar mass in the numerator. And then we have to divide both sides by 0.0784. Divide both sides by 0.0784. And the units for that is moles per kilogram. And so then we see that the kilograms will cancel. And then we are left with grams in the numerator and moles in the denominator, which is the units for molar mass. Right. And so then we have our answer. So when we push the buttons, we get 148. And so you get 148 grams per mole. They do it a different way, and that way works exactly the same. You have to do the exact same things. You've got to convert your grams, your milligrams into grams. You got to convert your grams of solute into kilograms of solute. And then you take and you get your grams divided by your moles. They get a number for moles. So they do it in more steps. I put it into how do I find molality? Every time I find molality, I take my mass, divide by my molar mass. That gives me my moles. And then I divide that by the kilograms of my solvent. That's the way I do it. So when they want me to solve for molar mass, I know I'm going to be given everything except for the molar mass. All right, you got sulfur. This one is an interesting one. You got sulfur, of course, a non-metal on the periodic table, dissolved in 40 grams of carbon disulfide, the boiling point elevation. All right. So now, again, it's not the boiling point. It is the boiling point elevation of the carbon disulfide was found to be 2.63. So that is your delta T sub B. That is your boiling point elevation. That's how much it went up. All right. What is the molar mass of the sulfur in the solution? All right. So the same thing, except here we have delta T sub B is equal to I K B C sub M. All right, and so they have to give us the KB. It is a constant. They do. And they gave us the delta T sub B. So the only thing we need to solve for is our molality. All right, and so if we solve for molality, we have our 2.63. That's equal to, this is an organic carbon disulfide. That's organic. You have a 1. You have the constant given to you, 2.40. And now you have your molality. So to solve this, you divide both sides by 2.40, divide by 2.40. All right, the degrees Celsius will cancel, and you end up with concentration, of course, in molality. And so then we have 11.2 grams of sulfur. All right, so then we have the exact same equation. So we're going to have our mass divided by the molar mass divided by the kilograms of our solvent. All right, so now we have this number, which is 2.63 divided by 2.40. So 1.1, whatever. And that is the mass, 11.2 grams. They're asking for the molar mass again. So we're again solving for this molar mass, which is a very common thing to ask for when you're doing a boiling point elevation or freezing point depression. And that was put into 40 grams of carbon disulfide. So in kilograms, 0.0400 kilograms. So once you find your molality from your freezing point depression, then it's exactly the same problem as we did on the previous example. All right, so I was really close with the 1.1. Anyway, well, it actually is exactly 1.1. So the correct sig figs here would be 1.10. All right. So again, moles per kilogram. The way you're going to find this is your mass divided by molar mass divided by your kilograms of your solvent. All right, so they want to find the moles of the solute, so they do it a little bit different. I like to put it in the same equation every time. They want to find the moles of solute, so they take the molality times the kilograms of your solvent. So once you have calculated your molality, Then they convert your grams into kilograms, and now you have your moles of solute. So what they always do is they solve for the moles, and then they take the grams and they divide by the moles, and that gives you your molar mass. So they take the 11.2 divided by the moles. All right. So once we got our answer, which should, to the correct sig figs, be 256 grams per mole, they said, what is the formula for sulfur? Okay, so this goes back to empirical versus molecular formula. So you take your N, which is going to be a integer, and remember, you take your molar mass divided by the empirical mass. And that's going to give you an integer. The molar mass, we just saw for the molar mass, it was 256. The empirical mass for sulfur, 1 sulfur, which was in the question. We are burning sulfur. We are doing the boiling point elevation of sulfur. So divide that by 32 and you get 8. And so your formula is S8. All right, so we had our 7 diatomics. All right, hydrogen, nitrogen, chlorine, fluorine, bromine, iodine, hydrogen, oxygen, nitrogen, whatever one I'd skip. But anyway, it makes a 7 on the periodic table, and then you got your hydrogen over there. You have P, which is 4, a tetramer, and you have an S that is 8, an octamer. All right, so this confirms that S is an octamer. All right, osmosis found in cells. You're going to have a semi-permeable membrane. What is meant by semi-permeable membrane is that it will let the solvent go through. It will not let the solute go through. All right, so you have a semi-permeable membrane. Only the solvent is allowed to go through. The solute is not allowed to go through a semi-permeable membrane. And so we're going to do osmosis, and the osmosis is going to go until you have the concentration on both sides to be the same in this semi-permeable membrane. All right, so you can set up a little demonstration. You can get a semi-permeable membrane, put it on this fancy funnel called a thistle tube. And in this thistle tube, you're going to put a bunch of glucose. So a glucose solution, a strong glucose solution. And in the beaker, you're just going to put pure water. All right, and so the only thing that can flow is your solvent, in this case, water. The water can go through the semi-permeable membrane. And it's going to go into the semi-permeable membrane until you get equal concentrations. All right, well, since the concentration of the glucose in the water is 0, we didn't put any glucose in the water. The water is going into this thistle tube where the concentration is high. You add more water and you dilute it, which means your concentration is going to go down until you have equal concentrations. All right, this will never have equal concentrations, so this will go on forever, but that's not true either. It is going to go up until it reaches a high enough pressure to where it stops. And when it reaches that high pressure and it stops, that pressure is called the osmotic pressure. That is the pressure where osmosis will stop. All right, and so here, you let it go over time, and it's going to go up the tube until you have a difference in pressure. Then this pi, this is your osmotic pressure. All right, so once it is high enough that the osmotic pressure, there it depends on your concentration, how high that's going to go. All right, every solution will have its osmotic pressure where osmosis is going to stop. So no more water is going to be going up. It will be going up, but as you see in this picture, as 3 molecules of water go up, 3 molecules of water go down because we are now in equilibrium. And so that pressure is not going to change. The pressure is always going to stay right here, so the height of this is not going to go any higher. So it's going to stay right here. But the water's not static, as shown in the picture. 3 water molecules go up, 3 molecules go down. And so you always have the same height for your osmotic pressure. All right, so again, they give an equation without an I in it. All of their equations should have an I in it. All right, and so this is how we're going to calculate osmotic pressure. This is easy to remember because although it's a gas law, PV is equal to nRT, which is what we are not using. We are not doing gases. We are doing solutions. But if you just look at the units, it works out perfect. So we divide both sides by V, and you got N over V RT. And so we know that N is moles, V is volume, and so when we have moles per liter, we have molarity. And so we see that the pressure is molarity RT. Now, once you have molarity, it has to be a solution. All right, and so again, with all of these, you need the I value to go in there as well. And so now instead of calling it P, we call it pi. All right, so we now know what everything is. M is our molarity. And remember, that's moles of solute per liter of solution. All right, and now with PV is equal to nRT, we always use the same R value, and we are going to use that same R value here, and that is 0.08206. We need liters, we need atmospheres, and mole, and Kelvin, which also leads us to our temperature, which has to be in Kelvin. All right, so don't miss this question because you did not convert your temperature into Kelvin. Anytime you have T, it is 100% of the time in Kelvin. Delta T, then that can be Kelvin or Celsius. But if it is T, it is Kelvin 100% of the time. All right, so we can calculate an osmotic pressure. All right, dextran. All right, it's not on the periodic table. I is 1. All right, so it's a polymer of glucose units. All right. We're at 21 degrees Celsius, so add 273, you got 294 Kelvin. What is the osmotic pressure? So we're looking for osmotic pressure. We want it in millimeters of mercury of a solution that has 1.50 grams of dextran dissolved in 100 mils of aqueous solution. And they have to give us the molar mass of dextran, which is 4.0 times 10 to the 8th. I never use AMUs. Grams per mole. All right, AMU, grams per mole, same thing. I never use atomic mass units. I always use grams per mole. All right, so now we have to take our 1.5, divide by our molar mass. That gives us our moles. We convert this into liters of solution. So pi is equal to I mRT. So we're looking for the osmotic pressure. We don't know what dextran is. We do. It's a bunch of glucose units. The I value is 1. Moles, 1.50 divided by 4.0 times 10 to the minus 8. That's moles per liter of solution. That is 0.1000 liter of solution. So that is our molarity. The R is the 0.08206 liter atmosphere per mole Kelvin. And our temperature is 294 Kelvin. All right, so once we have our moles, we then divide it by the 0.1 liters. That's our molarity. R will be given on the test, 0.08206. There will also be the 8.314. Make sure you know that you want osmotic pressure. You need to have pressure units. Do not use joules. That does not have pressure units. All right, so when we divided by the molar mass, we got our moles, and then we took that and divided by our 0.1 liter. And so this is our molarity when we take our moles divided by our liters. The I value is 1, and when you multiply those together, you get a very, very small osmotic pressure, 9.05 times 10 to the minus 7, even when you convert it to millimeters of mercury, make sure you know how to do that. Make sure you know this conversion. 760 millimeters of mercury is 1 atmosphere. So you have your osmotic pressure. It's still extremely small osmotic pressure. 6.9 times 10 to the minus 4 millimeters of mercury. That is an extremely small amount of pressure. All right, so when you look at, in biology, you have your different cells. Okay, so isotonic solutions. That means the exact correct amount of solution. So saline solution is a 0.9% sodium chloride. Your glucose solutions, 5% glucose. All right, so if you have the 0.9% NaCl, you have your 5% glucose, you have an isotonic solution, a physiological solution. All right, when you have a hypertonic, right, so you have your cell here, which has a semi-permeable membrane, and water flows out of the cell because hypertonic means you have a high concentration. So when you have a high concentration, let's say you got them messed up and you made a 5% sodium chloride because you thought everything was 5%, and so you made a 5% sodium chloride. That is a hypertonic solution. That concentration is way too high. And so your cell sees it's in contact with a solution that has a very high concentration. The water is going to flow out of that cell. It's going to shrink the cell. And that is called crenation. Now, if you go over here and you, instead of thinking everything was 5%, you thought everything was 0.9%, and you made a 0.9% glucose. All right, so now you have way too much water. All right, and now your cell has a higher concentration, and so the water is going to go through the cell into the cell because the cell has a semi-permeable membrane, and it's going to fill up because water is going to go in by osmosis, and if you get enough water going in, it will burst, and that is called hemolysis, where your cells burst. So this is all based on osmosis. And so important, very important in biology to know your physiological isotonic solutions where you don't have water flowing in or out of your cell. Well, they are, it's always at equilibrium, but you never have too much water in or too much water out. And there's the eyeball. All right, so now they finally put it into the correct. So all of your formulas, if you don't have the I's in them, you better have the I's in them, because if I asked sucrose, you would have it right, but if I asked sodium chloride, you would get it wrong, because in sodium chloride, all of these I values would have a 2 in it. All right, so all of these equations that they showed us the first time was all based on organic compounds, and they didn't put in the I value. I should always be in there. If it's organic, you put in 1. If it is a ionic solution, then you got to have more than 1. So if it is calcium chloride, the I value is 3. If it is calcium sulfate, the I value is 2, because that is a calcium plus 2 and a sulfate minus 2. All right, so make sure you come up with the correct I value from your ionic compound. If it's a compound you've never heard of before, then the I value is 1, because that is some organic compound. All right, so isotonic saline solution. All right, and so here is how you make an isotonic saline solution. All right, you take 0.9 grams in 100 mils of water. That's a little bit off. It should have been 99.1 grams of water. No, okay. All right, so apparently biology makes a 0.9%, and that is a mass volume percent. And so here we take our 0.9 grams, and then our 100 mils of water. When you do a mass volume percent, the mass has to be in grams, the volume has to be in milliliters, and then times 100, and you've got your 0.9% NaCl, which is your isotonic saline solution. All right, and so we have saline solution, which is sodium chloride, which means the I value is equal to 2. Now, the I value, we always will assume this. We will have the ideal value. All right, if once you have a very high concentration, the I value is not 2. That's as high as it can get, the I value of 2. As the concentration increases, the I value decreases, which means not all of the ions are going into solution at that point. But for this class, we are always going to assume whatever the formula is, that's how we get our I value. It's always the ideal value. All right, so what is the osmotic pressure? So pi is equal to I mRT. And so your I value is 2 because it's sodium chloride. There's one ugly 2. All right. That is a 2. Now we need to find moles per liter of solution. So we got to take our 0.9 grams and divide by 58.44 grams per mole. That's right, 35.45, 23.22.99, 58.44. Yeah. All right, and then our volume of solution is 0.1 liter. 0. And then the R, 0.08206 liter atmosphere per mole Kelvin. And then our temperature, 25 degrees Celsius to 98 Kelvin. Temperature always in Kelvin. All right, and here it doesn't say what units, so either atmospheres or you can convert that to millimeters of mercury. Osmotic pressure is usually given in millimeters of mercury. Doesn't mean it has to be in millimeters of mercury. It just usually is in millimeters of mercury. But in this case, we have such a very high osmotic pressure, 7.53 atmospheres, then atmospheres is fine. So it kind of depends on what your number is. If you got a 0.0 something atmospheres, they usually want it in millimeters of mercury. If you've got a high pressure, they usually just leave it in atmospheres. And note on the test, when this problem's there, you're going to have another answer that is a 3.76 atmospheres. And of course, that is the wrong answer, and that is when you don't put in your I value of 2, you just leave it as a 1. So make sure you have the I value in there when you have an ionic compound. Colloids, the Tyndall effect just means like fog is a colloid. If you have your headlights on in the fog, you can see where your headlights are going. And so the Tyndall effect is just it reflects these particles of a colloid are so big, it reflects light, and so you can then see light going through a colloid. All right, and so here in the yellow solution, you can't see the beam of light. It lights up, but you can't see the beam of light. And here over with the colloid, you can see how the light is going in and getting larger, just like a flashlight. You would see in the fog, you see that in this solution. So that is a colloid. So colloids just have a bigger particle in the liquid phase. Particles are so big, they reflect light, and you can see the light shine through. Versus your solution, you have smaller ions in solution or molecules in solution, and it does not scatter the light. Then we have a bunch of different types. You need to always be very familiar with the term hydrophilic. It means it loves water. Polar, loves polar. Hydrophobic, hates water. So hydrophobic things are non-polar because water is polar. All right, and so hydrophilic means it's going to be polar. Like dissolves like, polar and polar. Hydrophobic is going to be non-polar. All right, so non-polar and polar do not mix. They make immiscible two layers, and those are called non-polar things are called hydrophobic, which means they do not like water. All right, when you have a soap, and the way they write it in biology, I think they just put something like this. You got your phospholipid bilayer, and you got this, and it goes like that, something like, anyway. So what this is showing is you're going to have a polar head, and so here is your polar head, and then you're going to have your non-polar tail, and the non-polar tail is always an organic compound. This is a carbon-hydrogen compound. So that's CH2, that's CH2, CH2. So that is a bunch of CH2s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, plus this one, 18. So this one has carbon. So there's 18 carbons that go off of this polar head. All right, and that's how a soap is also going to work. You have the polar head, which is, of course, hydrophilic, and then you have your non-polar tail, which is, of course, hydrophobic. All right, and so the soap, all right, will form these micelles, which has all of the polar heads with the water, and then on the inside, you have this non-polar. All right, so if you have grease, oil on your hand, whatever, something that is non-polar, it gets surrounded in this micelle, and then it is flushed down the drain because the whole thing is soluble in the water. All right, so if you have dirty clothes, you got an oil spot, the soap comes in, and it will surround the non-polar oily spot, and then that then gets flushed down the drain. All right. So here, if we have green food coloring with our water and then vegetable oil, if you shake it up, you let it set, it's going to look like this. The higher density is going to be on the bottom, lower density on top. So your vegetable oil has a density less than 1. All right, and now if we put in some soap and then we shake it up. So when we put soap in there and we shake it up, you get what is called an emulsion. All right, and it doesn't separate back out into 2 layers. This emulsion is you have these oil droplets in these micelles, and they are in there. And this is called an emulsion, which is a colloid. These droplets that the micelles make are very large molecules, and they do reflect the light. All right, so all of your soaps are going to have some sort of polar head and non-polar tail. This is just another example of a soap. Another example of a soap. They all have a polar head and a non-polar tail. All right, so on the test, I think this, let me write on this. Note here when we did our, nope, I can't note that. Why isn't it showing? Showing on there, wasn't it showing on there? All right, so on exam 6 on Thursday, here is the equation sheet you're going to be given. All right, so the R value, both R values are given. When you're doing osmotic pressure, make sure you use the one that has the atmospheres in it. All right, so here's your osmotic pressure. The I value is put into this equation. So usually there's at least one osmotic pressure question. There's always a Clausius-Clapeyron equation here where you have to solve for a pressure at a different temperature. And we're talking about vapor pressure, so that's your delta H vaporization, which is in kilojoules. So you have to use the R value that has the joules. So this R value is osmotic pressure in atmospheres. This R value, you have to cancel the joules, so you have to have joules. This is your vapor pressure lowering. This should have an I here. The I values are put in for your boiling point elevation and your freezing point depression. And then below here, you see that you have the different melting points and your different boiling points and the constants for Kf and Kb. You got your Henry's law constant there. And then my favorite equation is the cubic equation here when you're dealing with a simple body and a face-centered cubic lattice. And then this is the length of a side for, well, this one is simple. And you got your body-centered and your face-centered. So this one is a little bit difficult. This is 2 square root of 2, and then R. The R is not under the square root. So you have to be familiar enough with these to know that that R is not under the square root. All right, so that is going to be given on the test. You don't need to memorize any of that. All right, so practice exam 6. You'll notice problem 3 is going to take us probably in a whole class period. So this is the hard part of the test is when you are calculating all of the different concentrations, molarity, molality, mole fraction, your mole percent, your mole fraction, your percents by mass, percents by volume, percents by mass volume. Lots and lots and lots of different kinds of concentrations. All right, so the one we're going to end on today is number 5. Freezing point of H2C2O4 is negative 1.80. Calculate the molality, calculate the boiling point, and calculate the mole fraction. All right, so they give you the freezing point. So it's aqueous, and so that means that it is from water. You have to know that water has a freezing point of 0. So the only one you have to know, although I think it's in the chart anyway, they list the ones for water. But you should not have to look up what's the freezing point of water. It's 0 degrees Celsius. You should not have to look up the boiling point. It's 100 degrees Celsius. It will be given, but you should know those. All right, so the freezing point is 0. So now the freezing point is negative 1.8. That means our freezing point depression, delta T sub B, is a 1.8. It went down 1.8. You also need to know the I value. This is an acid. It starts with H. It's an acid. All right. And when we did our net ionic equations, so we go to our acid, this is not one of the 6 strong acids. And so a weak acid always stays together. When it stays together, that means your I value is 1. All right. And so here you have a compound, which is an acid, but it's not a strong acid. It stays together. The I value is 1. All right. So to calculate the molality, we're going to use the freezing point depression. Delta T sub F is equal to I Kf C sub M. All right, so our delta T sub F is equal to I Kf C sub M. And so it went down 1.80 degrees Celsius. All right, this was a weak acid. The I value is 1. You look up on your chart for water, the Kf is 1.86 degrees Celsius per molal. And then we have our C sub M. All right, and so we have to just divide by 1.86. So 1.80 divided by 1.86, that is your C sub M, which is your molality. So that's going to be a 1 point, no, not 1 point, a 0.9 something. .968. All right, so that's moles per kilogram. All right, so that was part A. That's the molality. Calculate the boiling point. So now we got to calculate the boiling point. Now that we have the molality, we can calculate the delta T sub B. That's equal to I Kb C sub M. All right, so delta T sub B is equal to the I value. This is a weak acid. The I value is 1. Kb, we look it up on the table, 0.512. And the molality, we calculated the molality is 0.968. So delta T sub B is 0.495. All right, and so of course, that is definitely not the boiling point. That is the boiling point elevation. Delta T sub B is not the boiling point. It is the boiling point elevation. You know that water boils at 100, and so this is now 100.495 degrees Celsius. And the boiling point of water is a perfect 100. And so this looks ridiculous to give 6 sig figs, but the boiling point is an exact number for water. It is exactly 100 degrees Celsius. All right, so that is how you find the boiling point. It's a boiling point elevation, so we know it's going to be higher than 100. Delta T sub B tells us how much higher than 100 it is. All right, then we need to find the mole fraction. All right, so we have to find moles of your H2C2O4 divided by moles of H2C2O4 plus moles of water. All right, so this is where you're going to do this many, many times, that we have a molality. So our molality is 0.968. And you have to know the exact units. Moles per kilogram is not good enough. This is moles of the solute per kilogram of the solvent. All right, so we already have the moles here. We already have that same number goes here. All we have to do is convert kilograms of water into moles of water, plug that in there, and then we have our answer. So we have 1,000 grams of water divided by the 18.02 grams per mole of water, always divide by the molar mass. That is the number that goes there, which is a 55.5. All right, so you got your 0.968 divided by 0.968 plus 55.5. And that gives you a mole fraction to 3 sig figs of 0.0171. So that is your mole fraction of your weak acid, H2C2O4. Of course, the rest is water. So that is a 0.9829. All right, because we know that when we add these up, it has to add up to 1. So that's how you do number 5. So again, units, make sure you know the exact units. We will be doing the problems that we were starting on there. We'll do the rest of them on Tuesday and Wednesday. So if you get a chance to look at those, you can look at them. But we are going to go through those in class.